Today we're going to learn about the characteristic equation, which is basically going to be our way of finding eigenvectors or eigenvalues. Actually, the equation is going to give us the eigenvalues, and then once we know the eigenvalues, we can find the eigenvector. Here's the big thing that we have to notice. Every time we find an eigenvector, every eigenvector is actually one of many eigenvectors. So every eigenvector is one of an infinite number of solutions. And so if you remember this last time, we saw an example where our eigenvector was 1, 1, negative 1, I think, maybe, or 1, 1, I can't remember what it was. But then we also saw that we could have done 2, negative 2 for a vector, and we actually had lots and lots of vectors. And that's because we found the vector by solving an equation equal to 0, and we had some a yada yada and some vector, some matrix times x equal to 0, and we had solutions. We had non-trivial solutions. Okay, so if that's the case, then we can think a little bit about eigenvectors and what has to be the case for a matrix in order to solve it. So let's just go through and rederive that eigenvector equation that we've done many times. So an eigenvector with eigenvalue lambda satisfies, well, what does it mean to be an eigenvector? Well, to be an eigenvector, it just means that when you take the matrix and multiply it by that vector, that you get the same vector back except multiplied by some constant lambda. So that just means we have an eigenvector with eigenvalue lambda. So now let's do a little bit of algebra. I'm going to subtract this to the other side. We've done this a couple times already. And that's 0, but it's a 0 vector. Then we factor out the x. And that becomes a minus lambda times x equals 0. But notice it doesn't make sense to subtract a lambda, so I'm going to put an I right here. So a minus lambda I x equals 0. And so this is the solution that we have to have. And this needs, and what we do is we find the non-trivial solutions of this. Well, I want you to notice what that means. If this has non-trivial solutions, then that means that a minus lambda I satisfies that list of things. Well, actually, it doesn't satisfy the list of things. It satisfies all those requirements that are the same as being not invertible. Okay, so that's actually an important idea, because once we know that we have non-trivial solutions, that means it's not invertible, and that means we have a whole long list of things that are all must be true. Well, one of the things that must be true, and we saw this the last couple times, is that this means that the determinant of a minus lambda I, okay, think in front of me, what does this have to be? What we know is that invertible matrices always have a determinant that has a non-zero number. Not invertible matrices always have a determinant equal to 0. And this is what we call the characteristic equation. So this gives us a method for finding eigenvalues. So given any matrix, what you can do is you can just solve the determinant of a minus lambda I equals 0 to find eigenvalues. Okay, and this is a big idea, and this is a really useful idea. So let's do the first example together. Let's try example 5.6, and then you might guess how the rest of the day is going to go. The rest of the day is going to go where you get to do each problem, and then I'll make videos of them, and you can kind of check and see if you did them right or not. Okay, well, let's do 5.6 together. So 5.6, our matrix A is the matrix 2, -1, 1, and 4. And that means that if I come over to this equation, a minus lambda I, then I've got the determinant of a minus lambda I. Well, this is the same as the determinant of, well, this is our matrix here, 2, -1, 1, 4, and then minus the matrix lambda, 0, 0, lambda. And what you'll find is that writing down this step becomes a little unnecessary because each time it's just 2 minus lambda, -1, 1, and 4 minus lambda. And what you see is that you just do minus lambdas across the diagonal and every other number stays the exact same because that's what it means to subtract lambda I from it. Okay, well that's good. Now we can do this determinant pretty easily. So this becomes 2 minus lambda, 4 minus lambda, and then that's a -1, but it looks like +1 equals 0. And now it becomes an algebra problem. So now you're back in college algebra class. So what am I going to do? I'm going to FOIL this out and get 8 minus 4 lambda minus 2 lambda plus lambda squared plus 1 equals 0. Let's go ahead and do, let's put our lambda squared up front. Lambda squared minus 6 lambda plus 9 equals 0. So that looks like what we've got. Okay. So now we got lambda squared minus 6 lambda plus 9 equals 0, and that ends up being 1. That's a pretty friendly equation. This is lambda minus 3 squared equals 0, and so lambda equals 3. We've got only one eigenvalue for this problem. Did I mess? I didn't mess up, did I? For some reason, I thought when I wrote the problem, I thought I was going to get 2. Let's see, 8 plus 1 is 9, okay. -4, -2 is -6, and that's lambda minus 3. Okay, I think I did it right. So lambda equals 3 is the only eigenvalue. Okay, now once we have our eigenvalues, we can now, or eigenvalue, we can now find our eigenvector. So this is our eigenvalue. So let's go find our eigenvector. And our eigenvector is simply what we get when we solve that equation, when we solve a minus lambda I is equal to 0. So I'm just going to take 3 and put it in each one. And so we'll do 2 minus 3, -1, 1, 4 minus 3, and then we'll just set that equal to 0. So we're just solving a minus lambda I equals 0. This looks like we get the vector -1, 1, and then down over here, it looks like we've got -1, 1. Okay, well, good, that worked. And we've got 0, 0. And what you see is when you row reduce, the second row cancels. And in fact, every single time, the second row is going to cancel. -1, -1, 0, 0, 0, and 0. And so this allows us to find our solution. And our solution is simply -x minus y equals 0. So x equals -y. And if I want, I could write it as the matrix xy is equal to, well, x is going to be -1y and y is going to be 1. So -1, 1 is a good eigenvector. So or I could switch. I could have done 1, -1. You can scale this and multiply this by any number, and you get an equally reasonable eigenvector. So for this problem, we had only one eigenvalue. We got the eigenvalue of lambda equals 3 with an eigenvector v equal to -1, 1 or 1, -1 or something like that. Okay, so you can choose your favorite one. Okay, that worked really well. What I would like you to do is I'd like you to go and try the rest of these problems. Try 5.7, 5.8, 5.9, 5.10, 5.11. Some of them are quite interesting, and then some of them are not as exciting. But try each one and see how it goes, and then come back and look at the videos that follow this to see how they work. Okay, good luck.